Variation of pressure with depth. A fluid is at rest in a container. In the adjacent figure, point 1 is at height h above a point 2. The pressures at points 1 and 2 are P1 and P2 respectively. Consider a cylindrical element of fluid having area of base A and height h. As the fluid is at rest, the resultant horizontal forces should be zero and the resultant vertical forces should balance the weight of the element. The forces acting in the vertical direction are due to the fluid pressure at the top P1A, acting downward at the bottom P2A, acting upward. If mg is weight of the fluid in the cylinder, we have P2 minus P1 into A is equal to mg, equation 10.5. Now if rho is the mass density of the fluid, we have the mass of fluid to be m equal to rho v equal to rho A, so that P2 minus P1 is equal to rho gh. Equation 10.6. Pressure difference depends on the vertical distance h between the points 1 and 2. Mass density of the fluid rho and acceleration due to gravity g. If the point 1 under discussion is shifted to the top of the fluid, say water, which is open to the atmosphere, P1 may be replaced by atmospheric pressure PA and we replace P2 by P. The equation 10.6 gives P is equal to PA plus rho gh. Equation 10.7. Thus, the pressure P at depth below the surface of a liquid open to the atmosphere is greater than atmospheric pressure by an amount pHg. The excess of pressure P minus PA at depth h is called a gauge pressure at that point. The area of the cylinder is not appearing in the expression of absolute pressure in equation 10.7. Thus, the height of the fluid column is important in not cross-sectional or base area or the shape of the container. The liquid pressure is the same at all points, the same horizontal level with the same depth. The result is appreciated through the example of hydrostatic paradox. There are three vessels, A, B and C in the adjacent figure of different shapes. They are connected at the bottom by a horizontal pipe. On filling with water, the level in the three vessels is the same, though they hold different amounts of water. This is so because water at the bottom has the same pressure below each section of the vessel. In the experiment, it is found that the mercury column in the barometer has a height of about 76 cm at sea level, equivalent to 1 atmosphere, that's 1 atm. This can also be obtained using the value of P in equation 10.8. A common way of stating pressure is in terms of centimeter or millimeter of mercury, that's Hg. A pressure equivalent to 1 mm is called a torr after Torricelli. 1 torr is equal to 133 Pascal. The mm of Hg and torr are used in medicine and physiology. In meteorology, a common unit is the bar and the millibar. 1 bar is equal to 10 to the power 5 Pascal. Hydraulic machines. Let us now consider what happens when we change the pressure on a fluid contained in a vessel. Consider a horizontal cylinder with a piston and 3 vertical tubes at different points. The pressure in the horizontal cylinder indicated by the height of the liquid column in the vertical tubes. It is necessarily the same in all. If you push the piston, the fluid level rises in all the tubes, again reaching the same level in each one of them. This indicates that when the pressure on the cylinder was increased, it was distributed uniformly throughout. Whenever external pressure is applied on any part of a fluid contained in a vessel, it is transmitted undiminished and equally in all directions. This is the Pascal's law for transmission of fluid pressure and has many applications in daily life. A number of devices, such as hydraulic lift and hydraulic brakes, are based on the Pascal's law. In these, device fluids are used for transmitting pressure. In a hydraulic lift, as shown in the adjacent figure, two pistons are separated by the space filled with the liquid. A piston of small cross-section A1 is used to exert a force F1 directly on the liquid. The pressure P is equal to F1 by A1 is transmitted throughout the liquid to the larger cylinder attached with a larger piston of area A2, which results in an upward force of P into A2. Therefore, the piston is capable of supporting a large force, large weight of say a car or a truck placed on the platform. F2 is equal to PA2 is equal to F1A2 by A1. By changing the force at A1, the platform can be moved up or down. Thus, the applied force has been increased by a factor of A2 by A1, and this factor is the mechanical advantage of the device. The example below clarifies it.